We now take a look at IPv6 routing technologies in order to provide inter-network communication within IPv6 networks. The changes to the address architecture have introduced the need for routing protocols that are capable of supporting IPv6. Two such routing protocols include RIP-NG and OSPF-v3. The characteristics and operation of each of these protocols generally reflects those used in IPv4, however contain some distinct differences that are required to be understood to support the implementation of IPv6-based routing protocols within an IPv6-founded enterprise network. So upon completion of this section, it is generally expected that trainees will be able to describe the characteristics and operation of RIP-NG, describe the characteristics and operation of OSPF-v3, as well as configure RIP and OSPF routing protocols for IPv6. We begin here by taking a look at the next generation of RIP routing protocol developed to support IPv6 networks, that is aptly named RIP-NG. The protocol itself is greatly based on the same distance vector principles as are found within IPv4-based versions of RIP. However, the general behavior of IPv6 technologies introduces a number of additional features into routing. RIP-NG, as with IPv4-based versions, includes a diameter of 15 hops before it is considered that a network be subjected to count to infinity and deemed unreachable. A hop-based metric is also maintained, where each hop represents a cost of 1. Some of the major differences, however, include of course the change in addressing, where in IPv4 we implemented communication by assigning addresses considered to be in the same network range, which in an enterprise network typically consists of a private network range to consolidate IPv4 address usage. In IPv6, however, RIP-NG, as with all IPv6-based routing, facilitates communication between routers through linked local addresses, which we have shown here with the FE80 prefix followed by a 64-bit interface identifier. We find in this case that IPv6 global unicast addresses have been configured on end stations and routers. However, reachability primarily depends on the assigned linked local addressing, which is used to define the next hop for routes in IPv6. For example, a packet heading to the global unicast destination address of 2001::B that is found within RTB will be forwarded to the next hop of FE80::FE03:E24F. We additionally find that the advertisement of RIP-NG messages is now supported by the IPv6 reserved multicast address of FF02::9, which is the illogical equivalent of the RIP version 2 multicast address of 224.0.0.9. If we take a look at the format of the message header for RIP-NG, we find that the general format of the protocol contains fields similar to those found within RIP for IPv4, including the command field that specifies whether a RIP message is a request or response, the version, which for IPv6 is considered version 1 of RIP-NG, and routing table entries. For each routing table entry, the format is as we see below the main message header, with the IPv6 prefix defined along with the prefix length and relative metric for the hop. The RIP-NG messages are transmitted and received via UDP port 521, and each message may contain one or a list of routing table entries. To be able to implement IPv6 routing protocols, we must firstly enable support for IPv6 on the device supporting VRP. This is performed at the system view using the command IPv6. For each interface that is also to participate in IPv6, the command IPv6 enable must be configured at the interface view. Once complete, we are now able to implement IPv6 addressing on the enabled router interfaces. In this case, we are working with interface gigabit Ethernet 0/0/0 of RTA, to which we wish to allow the interface to automatically configure an IPv6 linked local address. To do this, we use the command IPv6 address auto link local, and in this instance, the interface has been assigned the IPv6 address of FE80::FE03:E24F. With the link local address applied, we can now implement RIP-NG routing on the interface using the RIP-NG1 enable command here, where the 1 represents the process ID, in the same manner as found within IPv4 versions of RIP. As a result of this, interface gigabit Ethernet 0/0/0 will now generate and receive RIP-NG advertisements and subsequently update the IPv6 routing table with any discovered RIP-NG routes, where peering routers such as RTB in this instance are also configured to support RIP-NG. In order for such IPv6 global unicast addresses or prefixes to be advertised, the same process is performed. In this case, we can see that an IPv6 global unicast address has been associated with interface loopback 0 on RTA, which is enabled to support IPv6 and manually configured to use the address 2001:1:1/64, and for which the interface is enabled to support RIP-NG. This IPv6 global unicast address will be as such advertised to peering routers via the link local address associated with interface gigabit Ethernet 0/0/0. In respect to the RIP-NG configuration that we have just implemented, the display RIP-NG command can be used to validate that the configuration has taken effect. Through this display command, we will also notice other similarities to the original IPv4 versions of RIP, including the preference and periodic update timers. For the configuration performed, however, we can identify that actual routes discovered is 1, which relates to the configured IPv6 global unicast address prefix of 2001:1:64. Along with RIP-NG, we also find OSPF is supported within IPv6 through OSPF v3. As with RIP-NG, link local addresses are assumed to be assigned to each of the physical interfaces in order to support IPv6 communication. The link local address is then used as the next hop address in order to reach the associated routes. OSPF v3 supports many of the same principles as found within OSPF v2 that is used to support IPv4 link state routing. We show here based on the broadcast network type in which a designated router is required, for which we find that the reserved multicast address of FF02:5 is applied. This is similar to the 224.0.0.5 multicast address found within OSPF v2 in order to support the advertisement of routes, to which all routers supporting OSPF v3 are expected to receive. Within IPv4 networks running OSPF v2, we would generally find that neighbors connected to broadcast NBMA or point-to-multipoint links were identified based on the IPv4 interface address, and of the network types we have looked at, only neighbors on point-to-point links were identified by their respective router IDs. In OSPF v3, however, we find that neighbors associated with all network types are now identified based on their router ID. The router ID will also continue to act as the decision maker when electing a designated router for multi-access network types, for which the all D router's multicast address of FF02:6, which similarly to the 224.0.0.6 multicast address in OSPF v2, is used by the DR and BDR. In terms of managing such DR and BDR, the priority value remains in use, to which a priority of 0 represents a specific interface should not take part in the DR election process. Another defining difference within OSPF v3 is the support of what is known as per-link behavior, as opposed to per-interface or per-subnet behavior that is found within OSPF v2. We can understand a link being roughly the layer below IPv6, which in the case of Ethernet may connect to many hosts. We show in this example from the perspective of RTA how the Ethernet network represents a single link, but to which communication with 3 separate peers is achieved. Each interface in OSPF v2 is found to be associated with a given IP subnet that is used to facilitate communication between the neighboring routers. We find now, however, that within OSPF v3, processing is performed on a per-link basis rather than per subnet, which allows communication between end stations over a link even if they do not share a common IPv6 prefix. We see the results of this through the OSPF v3 hello packet, which no longer carries address information, but instead contains an interface ID that is used to reference the interface on the link for the given router. We find that authentication is also no longer directly supported within OSPF v3. The primary reason for this is that authentication is now directly supported through IPv6, that now employs the authentication header and encapsulating security payload protocols within the extension header fields of the IPv6 header. We can see an example here of how OSPF is generally encapsulated within the IPv6 header. The IPv6 next header field will generally reference the authentication header or encapsulating security payload that is used to provide the security features required within the IPv6 header. The implementation of OSPF, as with RIP-NG, requires that IPv6 be enabled within the router initially, following which the OSPF v3 process can be enabled. In this instance, we only configure the command OSPF v3, for which the default process ID of 1 is created, as we can see in the parenthesis displaying the current OSPF v3 view. A router ID is then required to be configured to distinguish the router from other routers in the network, and also as a means to determine the designated router for multi-access network types, where the DR priority is equal for interfaces on the same link. For the link on which the peering routers are to establish an OSPF neighbor relationship, we must firstly enable IPv6 and configure the link local address. Previously, as part of the RIP-NG configuration, we used the IPv6 auto-address link local command to demonstrate how a link local address can be automatically generated for the interface. In this instance, however, for OSPF v3, we show how the link local address can be manually configured, for which we use the address FE80::1. We then associate the interface for the link with process ID 1 and area 0. We are also able to configure an IPv6 global unicast address on interface loopback 0 and advertise this network through OSPF v3 by once again enabling IPv6, configuring a global unicast address on the interface and associating this with area 0. Once basic configuration of OSPF v3 is complete, we are able to use the command display OSPF v3 to view the results of the configuration. Most notably, we find that the process is enabled with the router having been assigned the router ID of 1.1.1.1. If configuration of OSPF v3 has been successfully completed on the peering router, we should also find that a full adjacency with the neighbor is established, which is validated by the number of full neighbors showing currently as 1. So to summarize this section on IPv6 routing technologies, we just have two questions here. The first asks, what is the port number that is used by RIP-NG for listening for route advertisements? Well, if we recall, RIP-NG uses UDP port 521 in order to listen for route advertisements. And what is used to uniquely identify each neighboring node running OSPF v3? Well, a 32-bit router ID is used in order to uniquely distinguish each neighboring node running OSPF v3, while the interface ID will distinguish the interface on the link, where the router may have multiple interfaces associated with the same link.